All right, so let's try to solve some problems from Fourier transform. Majority of these problems are going to be from the properties that we've discussed. Some of them may be a little bit challenging, some of them may be easy, and there's some which have applications, and I'm going to try to refer to what applications these correspond to, right? So, सबसे पहले, I just want to build on top of the problem number one. Actually, let me repeat that here, which was uh, which was that of amplitude modulation, right? So amplitude modulation, we said, if this is uh, x of t is a signal, right, and I multiply that x of t with say cosine omega naught t, and what I get at the output is y of t. The question was, how is the Fourier transform of y related to the Fourier transform of x, right? There are a couple of ways you can do this, and we so let me do it two ways. So the first one, as we did in the end of last class, was kg y of t is equal to x of t cosine omega naught t, and therefore this is x of t times e raised by j omega naught t times half plus half x of t e raised by minus j omega naught t, right? And as a result, y of j omega, I just use the frequency shifting property. This is equal to x of j omega minus omega naught and plus half x of j omega plus omega naught. And as a result, what we concluded was if x of j omega looks something like this, right, which is which has a bandwidth of plus b here and minus b here. So here's the cutoff. So it's a band limited signal, right? And this is x of j omega. What would y of j omega be? Y of j omega is just simply going to be something that looks like this. So this is omega naught, and this is omega naught plus b. This is omega naught minus b. In here, this is the same shape. So shifted by omega naught to the right and shifted by omega naught to the left. This is minus omega naught plus b, and minus omega naught minus b, and this is y of j omega, right? And the amplitudes of course are half of what they were. Okay, and you could also prove this, by the way, through the multiplication property, and which we actually did at the end of the last class. How is that? Cosine omega naught ka Fourier transform is two delta functions, one residing at plus omega naught, the other one is minus omega naught. So multiplication in the time domain is convolution in the frequency domain. So therefore, if you convolve with a delta residing at plus omega naught, that just translates to a shift, and therefore this also shift at the negative frequency. Okay. So this is what we ended, I think, in the last class. The question now is, KG, what do you do? What can you do for you to be able to recover x from y, right? So actually what happens is, KG, this for example would be radio transmissions or AM transmissions, which would go into the air through a channel, and there will be some noise added to it, which would, let's say, be n of t, and this is what you would receive. This is the r of t, or the signal that you receive, right? And now you want to do something here. You want to do something here which ensures, KG, you can recover x of t back from r of t. And there are many ways of doing it, but let's try to figure out just one of those. For simplicity, let's assume so for simplicity, let me assume that the noise is 0. And noise analysis, I mean, how does noise affect the received signal? I mean, that's something you can study in your next semester. But let's assume for now, for simplicity, that the noise is 0. And we just want to see how can you recover x of t from r of t, right? And the answer actually lies in the frequency domain, right? So if n of t is 0, if this is 0, so then this r of t is actually equal to y of t. So what you receive is a signal y of t. The Fourier transform for this, for which looks like this signal here, right? Which is this shape here. Just the actual Fourier transform of x has been preserved, except that one of the copies lies at plus omega naught and the other copy lies at minus omega naught. Okay, so that's what's actually going on. Um, one important thing I forgot to mention, which was the omega naught here is actually much greater than b. Right? Why do I need this condition here? अगर ये condition ना होती तो what would have been wrong with the depiction of y of j omega? कौन बताएगा? जी तला.
It could have been like opposite side पे जा सकता था. Omega naught minus b would have been on
Yes.
the positive side.
Good.
अगर b larger होता.
Right. So they might have been overlapped in the two copies. Right? If omega naught was small compared to b, तो जब ये इधर this thing, when this copy, when it goes here, this would have actually been something like this, as Talha points out, right? और ये दूसरी वाली जो copy है वो इधर होती, and then these copies would have been overlapped and they would have actually interfered and they would have merged together. Okay, that would have been a hard problem to solve. I mean, actually you would not have been able to recover the signal here. Again, because omega naught is much greater than b, the two copies, one residing at plus omega naught, the other one residing at minus omega naught, they are identical and they are separated from each other. That's why the assumption is that omega naught is much greater than b. And it actually is, right? So typically आप जब so for example Wi-Fi may, the bandwidth, which is b here, is actually, if I'm not mistaken, 20 megahertz, right? But the carrier frequency is 2.4 gigahertz, right? So it's orders of magnitude greater, right? 100 times greater. Talha, आपका क्वेश्चन है कोई या? Okay.
No, sir, sorry.
All right. Now, the question now once again is, okay, how do you recover? How can you recover x of t, or x of t from y of t? And the answer lies in the frequency domain once again, right? So the question is such that, so if n of t equals 0, that means such that the received signal is actually equal to y of t, right? So the question is, how can you recover x of t from y of t? Any ideas? किसी का कोई आइडिया? Right, so what you want to do is, somehow if I can try to bring this copy down, right, and slash or, can I try to bring this copy up, right, in the frequency domain? Remember, everything is going on in the frequency. My analysis is going on in the frequency domain, right? So what kind of an operation could I do which would ensure कि यार ये कॉपी जो है पीछे आ जाए और ये वाली कॉपी आगे चली जाए? Among other things, maybe, और भी कुछ हो जाए. Any ideas how can I shift this in frequency? Right?
So shifting property.
कौन सी property? Shifting property.
Yeah.
Right. So frequency shifting property in the time domain is actually multiplying by complex exponential. Right?
Hmm.
And people sort of figure out here, what if I multiply this y of t once again with cosine omega naught t. तो फिर क्या होगा? So say कि let z of t be equal to this y of t times cosine omega naught t, where omega naught is actually the same frequency that was being used at the transmitter, right? So then what would happen then? Then what would happen is that z of j omega as a function of y of j omega. I'm not going to do the analysis here. I'll let you do it on your own. But I'm just going to try to explain it in words here. So z of j omega in terms of y of j omega क्या होगा? वो y of j omega की पूरी कॉपी नीचे आएगी एक और पूरी की पूरी कॉपी ऊपर जाएगी, right? So when it's actually brought down, what happens is कि ये वाली कॉपी पीछे आती है और ये वाली कॉपी और पीछे चली जाती है, right? So that's one thing that's going to happen. And what else is going to happen? When it's brought up, this is going to come here and this is going to go there, right? Intuitively speaking, right? So these two copies, because of e raised to power plus j omega naught, go up, and because of e raised to power minus j omega naught, t time goes down, right? और जो नीचे आ रही कॉपी और जो ऊपर आ रही कॉपी, they both overlap on top of each other, and when they overlap, they just add up. और जो ऊपर कॉपी चली गई है, वो that's something that needs to be removed, right? So that's how you would use Fourier analysis, and I think that all of this analysis is there in the textbook, right? What I would do instead is I just use trigonometric identities. I mean, so that was sort of an explanation of what goes on in the frequency domain, but I will just use trigonometric identities. I know the y of t is x of t times cosine omega naught t, right? And then I just multiply it with the cosine omega naught t again, right? And this gives rise to x of t times cosine squared omega naught t, right? So remember, this is y of t. This was y of t. And what happens here? I can use the trigonometric identity, which is cosine square theta is 1 plus cos 2 theta divided by 2. So this is x of t times 1 plus cosine 2 omega naught t divided by 2. And therefore, z of t turns out to be equal to, so I have been able to get x of t, albeit with the half attenuation by a factor of 2, and plus half x of t times cosine 2 omega naught t, right? So the z of t, I've learned here. Let's try to do this. जो भी आया ना यहाँ पे, let me just multiply this with a cosine omega naught t again at the receiver. And what I get here is actually half x of t plus half x of t cosine 2 omega naught t, right? So is this what I wanted? Of course, this is not what I wanted. I wanted actually x of t, और x of t के साथ एक और चीज भी शामिल है इसके अंदर, right? Can I get rid of the other thing? I mean, this is actually what was desired. This was desired, and this is undesired. Oh, oopsie daisy, sorry. So the first term was desired, and this was desired. And this thing here is an undesired term. I mean, this needs to be somehow cancelled out or nulled out, or let me use a term which is going to give us to or filtered out of this, of the received value. How do I filter this out? I mean, what do I mean by filtering it out?
वैसे एक since cos का there is a cos in it, हम एक filter बना सकते हैं. So
Yeah.
the filter is it. उसकी जो particular frequency होगी, we just make a filter that is going to filter particular frequency out.
Okay.
And बाकी हमारे पास जो signal बचेगा that would be
Right. So once again, the key is frequency domain analysis or Fourier transform, right? I just multiply by cosine 2 omega naught t. I don't really know what's going on, but let's just analyze this in the frequency domain. And in the frequency domain, I figure out here if I just look at z of j omega, z of j omega is equal to half times x of j omega and plus half times x of j omega minus 2 omega naught. Actually, this is 4 plus 1 by 4 x of j omega plus 2 omega naught. And if I sketch this z of j omega out, this z of j omega is going to have a copy of my desired signal, albeit scaled by a factor of 2 here. And then there's going to be a high frequency copy residing at 2 omega naught. And oops, give me a minute. Right. So residing at here. And then there's another copy which resides at the negative side. Right. So this is here at minus 2 omega naught. And this is plus 2 omega naught. And this is x of j, this is z of j omega. अब मैंने निकालना है blue वाली copy है, so what do? I just use a low pass filter, right? So because of the convolution thing that we studied, right? So therefore, if I can just employ a low pass filter here, right, which can cancel everything in the high frequency domain, I should be able to extract my signal, originally intended signal, right? So if I go back and I say, let me feed this into a low pass filter. If I do that, an ideal low pass filter, I should be able to get half of x of t out, right? And this is the demodulation procedure, right? Or the receiver, this is how the receiver is going to work, right? So this would be this side here is going to be the transmitter. And this side here is going to be, including the low pass filter, is a receiver. Okay, any questions here? And the bottom line once again is in order for us to be able to determine that x of t can be recovered using these principles, we had to go back and resort to using concepts of Fourier transform, concepts in the Fourier domain. And that's how we say कि this separable or filtering हो सकती है, and I'd be able to separate them out. Okay. And by the way, this low pass filter is an LTI system. जिसका frequency response is the square pulse. Okay. कोई question पूछा था जी दला.
Sir, I just need to confirm something. ये जो low pass filter होता है, so your frequencies are all those that are closer to 0, right?
Low फिर से बताइए.
Actually, I was confused about it, and I think I just got it. Okay, your frequencies are all those that are closer to 0. And actually, what was in my mind, negative side would also mean low. So basically, the negative frequency, so जिसमें frequency का absolute value ज़्यादा होगी, that would also be a high frequency.
Yes.
So the negative is also the negative just means its direction, right?
Yes. Exactly.
So
right. So
ignore the sign. We just take the absolute value, और उस हिसाब से वो pass filter बनता है.
Yeah. So all of these are low frequencies. Right. So the sign doesn't matter as far as saying this is low or high. I mean, the absolute value matters.
I've been confused about it for a while. Okay, low frequencies mean negative side is negative, but the numbers are lower, smaller.
Because as far as low frequencies are concerned, this is the rate of oscillation, right? So the rate of oscillation at plus omega naught is exactly the same as minus omega naught. It's just the direction is different. Okay, so minus sign is just incorporates the rotation direction.
Yeah, I get it. Thank you.
All right. Achha, let me try to build on top of this now, right? So or up the game, if you will, right? Let me say now, KG, there's x1 of t, which I multiply by cosine omega naught t. And then there's another signal x2 of t, right? There's something else that I want to transmit as well, which I multiply by sine omega naught t. And then what I do is I just add them up. And this is what I transmit over the air. Okay, and this would sound very intriguing or confusing, KR, if there are two signals of interest x1 and x2, and you're somehow you're multiplying something with that, and then you're adding things up. I mean, in general, when you add two signals up, I mean, there's no guarantee that you're going to be able to separate them out, right? I mean, addition in general is not reversible, right? But it turns out that there's certain properties of the cosine and the sine which allows us to do that, right? And we see kg, once again, let's assume kg there's no noise, and the y of t is exactly, or the received signal is exactly what was transmitted. So how do I separate x1 and x2? I need to estimate, or I need to recover x1 and x2 separately, right? So for that, what we do is we multiply with the cosine. Let's see what happens if I multiply with the cosine, right? And let's see what we get, right? So let's say this is z1 of t, right? You could do Fourier analysis to analyze here what z1 of j omega is as a function of x1 of j omega, x2 of j omega. I would rather just begin with some trigonometric identity. So z1 of t is y of t times cosine omega naught t, right? And y of t is equal to x1 of t cosine omega naught t plus x2 of t sine omega naught t times cosine omega naught t, right? So the thing inside the bracket is actually y of t. And let me expand this brackets now. So this is x1 of t cosine squared omega naught t plus x2 of t times sine omega naught t times cosine omega naught t. Okay. And now I can actually, I claim here, I mean, it's x1 and x2 can be separated from each other. How? By just analyzing what is going on in the frequency domain. So z1 of j omega is actually, or chalo, let me apply something here. So this is x1 of t, cosine square omega naught t is 1 by 2 plus 1 by 2 cosine 2 omega naught t, and sine omega naught t times cosine omega naught t, right? So that's sine theta times cosine theta. That's actually 1 upon 2 sine 2 theta, which is sine 2 omega naught t. Right? So I've used the trigonometric identity, which is sine theta times cosine theta is half sine 2 theta. And then I analyze what's going on in the frequency domain. So z1 of j omega is actually equal to half x1 of j omega plus half x1 j omega minus omega naught plus half x1, actually this is 2, x1 j omega plus 2 omega naught. And what about the sign here? Anybody who can help me, okay, if I multiply with the sign, what happens in the frequency domain? कौन बताएगा? No one? So what happens if I multiply with the sign? And what happens in the frequency domain? right? So let's do this here, right? So I just want to see here, ye kya hai, right? So this is equal to 1 upon 4 j x2 of t e raised to power j omega naught t minus 1 upon 4 j x2 of t e raised to power. So this is actually 2 omega naught t. So this is 2 omega naught t, and this is minus j 2 omega naught t, right? I can I go in the frequency domain? Of course I can. So the Fourier for this, the Fourier of whatever this is equal to 1 upon 4j x2 of j omega minus 2 omega naught minus 1 upon 4j x2 of j omega minus 2 omega naught, right? So once again, these are copies of x2 in the frequency domain, but they are residing at very, very high frequencies. I mean, centered at 2 omega naught and centered at minus 2 omega naught, right? So here's what I can do. So this is, I'm just writing whatever we did there. So this is 1 upon 4j x2 j omega minus 2 omega naught and minus 1 upon 4j x2 j omega plus 2 omega naught. Right? So can I now filter out x1 of j omega from here? And the answer is yes, right? So all of these components here, and these components here, and these components here, and these components here, they're all high frequency components. They're all centered at 2 omega naught, right? So if I just apply a low pass filter with center frequency 0 and the cutoff equal to the bandwidth of the signal, then I should be able to get x1, right? So this implies the x1 of t is just simply equal to just passing this through the low pass filter. This is z1 of t, right? So if I go back to the block diagram, if I just pass this through a low pass filter, which has a cutoff equal to the bandwidth of the required signal, of the desired signal, I am going to get x1 of t, which is extremely interesting or awesome, if you will. Here we had two signals mixed up together, and we've been able to identify a method where things mix, but not quite, right? So they are separable, right? Through these operations that we've been able to identify with the help of Fourier transform. And similarly, I'm not going to do this here. I'm going to leave off as something for you to think about. What if I multiply this with sine omega naught t? This becomes z2 of t, and it turns out that when z2 of t को low pass filter में से गुजारेंगे ना, तो you will get x2 of t. Right? So things are separable, easily separable, right? Now this is used a whole lot in communications. And also what you've actually been able to do, you have two simultaneous streams, right? Two simultaneous streams, x1 and x2. There's data in x1, there's information in x1, there's information in x2. And you've been able to transmit both of them simultaneously, right? Using the same bandwidth, right? Using the fact that एक cosine के साथ modulate हुआ है, एक sine के साथ modulate हुआ है. And that allows you to separate them out. And this is also an extremely important result that you'll end up using in the next semester when you study communication system. Okay. But the bottom line is that we've been able to use Fourier analysis to do all of these things that we did. X1 के साथ separable है, x2 के साथ separable है, we find out through Fourier analysis, right? There's one little point I just want to quickly gloss over, which is that of complex signals. So typically, we use the following model. So we say that x of t is equal to x1 of t plus j times x2 of t, right? So where this x1 was the cosine branch, right, and the x2 was the sine branch, हम क्या करते हैं in communication analysis, we say let's cook up a complex signal now, right, where the real part is x1 and the imaginary part is x2, and of course I'm assuming that these are real. X1 is real and x2 is real as they are in the real world, right? But my concoction here is, let me think of a complex signal which has the real part equal to x1 and the imaginary part equal to x2, right? So that my things become easier to analyze, right? And you can actually verify from here that y of t, which was actually being transmitted through those two branches, turns out to be just equal to x of t times e raised to power j omega naught t, and you just take the real part for that. Okay. Um, um, most likely this is so, right? So there's a minus sign, I forget. Right. So you can go ahead and verify is there a mistake here or not. But what I'm trying to say here is this is just tip of the iceberg in explaining why complex signals are so useful. It turns out कि जो भी पूरा का पूरा मैंने analysis इतना लंबा चौड़ा किया है, if I use complex signals and with some additional insight into it, it turns out that analysis can just be broken down in a single branch. And with multiplication with complex exponential cosine sines को अलग-अलग treat करने की जरूरत नहीं है. But I don't want to go there in those details. But I just wanted to mention this here. This is one area where complex signals are so useful. Okay. Any questions here before I?
सर आपने कहा था कि in real world we only have real signals. So how is this how is this signal going to exist? This imaginary signal going to exist when we are transmitting it?
Yeah. So like in real signals or complex signals is construction, right? It's a mathematical construction, right? Which makes our analysis a lot easier compared to the case when we were only dealing with real signals. Okay? And this is one of those applications. I do not want to go into a lot of details here, कि वो किस तरह आसान करता है, right? But just take my word for it.
My question is like, how does it exist? What does this mean? ये जो imaginary signal है, like what does it? How does it exist in our real world? What does it mean here?
Right. So देखिए जब भी complex signals की बात आती है ना, तो complex signal would have a real part and an imaginary part, right? And the real part would be a real signal, and the imaginary part would be a real signal, right? So typically, when we use complex signals, we use them for those applications in which there are actually two simultaneous real signals coming in on two separate branches. Okay? And instead of you dealing with them separately, saying कि जी एक x1 है और एक x2 है, मैं इसके ऊपर अलग प्रोसेसिंग करता हूँ, ऊपर वाली ब्रांच के ऊपर और नीचे वाली ब्रांच के ऊपर अलग प्रोसेसिंग करता हूँ, typically we lump them together into a complex signal of this form.
Okay, so originally वो दोनों real ही होते हैं, but inside our machine we just consider one of them to be
inside my construction, inside my mathematical construction, I do that, an equivalent construction. ठीक है? And what that construction is? Construction ये होगी यार x of t को मैं सिर्फ ये multiply करता हूँ. This e raised by j omega naught t, bas.
Omega naught t.
Right? So this would be my representation for those two parallel branches that I drew in the up above. ये अभी आएगी आपके पास, right? This here on the left hand side, right? These two branches, right? I say, let me just if I use complex number or complex signal representations, I can just represent that equivalently by this single branch here. Okay? And that makes my life easy. And this is just a tip of the iceberg. असल में आसान और बहुत सारी चीजें हैं जो बहुत आसान कर देता है. ठीक है? But I don't want to go there. For maybe another course somewhere. Okay. So what I want to do next is is something related to the exam and just applying Fourier transform. So exam 2 में कुछ problem था, something related to that, right? So here's problem number 3. X of t is equal to cosine omega naught t plus sine 2 omega naught t plus cosine 3 omega naught t plus sine 4 omega naught t, right? And it's fed into an LTI system. So that's something we know. So it's fed into an LTI system. And the output of the LTI system is, let's say, denote that by y of t. And the LTI system is a system which has a frequency response given by the following expression. H of j omega is equal to 1. Actually, the magnitude of h of j omega is equal to 1 for all frequencies between minus omega 2.5 omega naught and plus 2.5 omega naught, and is 0 otherwise. So this is the magnitude, and the phase of h of j omega is given as j times 0.2 omega over omega naught, right? So the phase is linear. And why is the phase linear? Let me make that explicit. Because the phase linearly increases as omega increases, right? So that's why we say the phase is linear. Now the question is, okay, what is the output, right? So, I mean, had you just the knowledge of Fourier series, this would have been very easy. I mean, you could have just used the fact that complex exponentials are eigenfunctions of LTI systems, right? So that's one way to do it. I would rather just use now the Fourier transform, right? So let's use the Fourier transform along with that multiplication property or the convolution property to determine what the output is. Okay. So for that, सबसे पहले I need to determine what the Fourier transform of x of j omega is, or x of t is, right? So what is x of j omega? So x of j omega is are such just a bunch of impulses. I'm just going to sketch this out. I'm not going to write this out, right? So if this is omega, and we're plotting x of j omega, x of j omega is equal to an impulse residing at omega naught, and the height is pi by 2. Actually, pi, height is pi, sorry. There's another impulse residing at minus omega naught, which is at height is pi. And then there's an impulse residing at 2 omega naught. The height is pi by j. There's an impulse residing at minus 2 omega naught, and the height is minus pi by j. And 3 omega naught. The height is pi, minus 3 omega naught, height is pi. And then there's a 4 omega naught, pi by j, and minus 4 omega naught. Which is minus pi by j, right? All I do is just compute the Fourier transform, right? Something we've done in the very beginning. So this is x of j omega. And what is y of j omega? Y of j omega is just simply equal to x of j omega times h of j omega. And I know that h of j omega is 0 outside of the interval minus 2.5 omega naught and plus 2.5 omega naught. So what happens? क्या होगा? So this is, here is minus 2.5 omega naught, and here is plus 2.5 omega naught. तो क्या बच जाएगा, क्या नहीं बचेगा? What do you think? Right, so these two impulses will be filtered out because of the fact that h of j omega is equal to 0 here. Similarly, these two pulses will be filtered out here as well. Because the frequency response of the system at these frequencies is 0, right? And then all you're going to be left with are these four impulses. Okay? So y of j omega is going to be equal to, and let me now write this out, right? So this is pi delta omega minus omega naught plus pi delta omega plus omega naught minus or plus pi by j delta omega minus 2 omega naught, and then minus pi by j delta omega plus 2 omega naught times h of j omega. And what is h of j omega? H of j omega is equal to this thing here is equal to h of j omega absolute, let me use the polar form, times e raised to power j phase h of j omega. And I know that within the frequency minus omega naught and plus omega naught with which I'm multiplying, or minus 2.5 omega naught plus 2.5 omega naught, this is equal to 1. And this here is equal to 2 times j times point, right? So this is 0.2 times omega by omega naught, right? So I made a mistake here. There's no j here. Okay, so therefore this is equal to pi delta omega minus omega naught times e raised to power j 0.2 divided by omega naught times omega plus pi delta omega plus omega naught times e raised to power minus j, actually still plus j 0.2 divided by omega naught times omega plus pi by j delta omega minus 2 omega naught e raised by j 0.2 omega by omega naught minus pi by j delta omega minus 2 omega naught e raised to power j 0.2 omega by omega naught. फिर क्या होता है? So what is delta omega minus omega naught multiplied by this exponential? Right? What is this thing here multiplied by this thing here? What do you think? Okay, so this is
सर वो उसकी भी फेज शिफ्ट हो जाएगी.
phase shift हो जाएगी. So this is
e
just
raised to
the
power omega naught हो जाएगा.
sampling
e raised to
property.
power j 0.
Yeah, so this is just the sampling property of the delta
e raised to
function.
power j 0.2.
Yeah, exactly. Right, so omega is going to cancel with omega naught. And this is going to be, यहाँ पे क्या होगा? Minus j 0.2, right? And then this is going to be pi by j delta omega minus 2 omega naught e raised to power, यहाँ पे क्या होगा? This will be 0.4, right? And then minus pi by j delta omega plus 2 omega naught e raised to power minus j 0.4, right? And then if I need to compute the inverse Fourier, how do I compute the inverse Fourier for this? Right, so this is y of, so what would y of t be? So what is the inverse Fourier transform for this signal here? Right, turns out this is equal to half e raised to power j omega naught t, and then this is e raised to power j 0.2 because that's linearity, and then I can just go on and on. So this is e raised to power minus j omega naught t, and this is e raised to power minus j 0.2. This is half 1 upon 2j. This is e raised to power j 2 omega naught t times e raised to power j 0.4, and then minus 1 upon 2j e raised to power minus j 2 omega naught t times e raised to power minus j 0.4. Okay, can this be simplified further? And this is more or less following the same principles or same steps that were required in the exam too. Is this simplifiable? Can this be simplified further?
Yes, sir. It's positive and negative.
Huh?
So we can either turn it into cosines,
Yeah.
or we can check सिर्फ real part इनका आ जाएगा.
Actually, good, right? So the real part cosine yaad hai, right? So this is actually j omega naught t plus 0.2 here, right? And this is half e raised to power minus j omega naught t plus 0.2, right? And this is 1 upon 2 j e raised to power plus j 2 omega naught t plus 0.4, and minus 1 upon 2 j e raised to power minus j 2 omega naught t plus 0.4, right? So I just do this simple manipulation, and these two things combined together, these are actually cosine. This is cosine omega naught t plus 0.2, and the other thing was, ये क्या होगा? This is sine 2 omega naught t plus 0.4. Okay, and I can slightly, this is omega naught t plus 0.2 divided by omega naught, and plus sine 2 omega naught, and this is t plus 0.2 over omega naught, and this is y of t. So if you just compare y of t with x of t, I mean, there's a very interesting relationship that you will find. And that relationship is कि एक तो high frequency components बिल्कुल cancel हो गए, right? So that been they completely go away. और जो low frequency components हैं, they stay exactly the same the way they were, except that they have been delayed, right? The low frequency components are a delayed version of what they were in the input. But the delay for the omega naught frequency is exactly the same as the delay because of the delay that the 2 omega naught frequency experiences, right? So there's the same delay, right? So this delay and this delay, they are the same, right? And this is actually, now you can try to think about it a little bit more. This actually comes about because of the fact that the phase was linear in frequency, linear in omega. If that was not linear, things would have been different, right? And for this, I just say, okay, try the above problem with the phase of h of j omega being equal to 0.2 by omega naught times omega squared. And you would have found out, and the magnitude stays the same, you would then find out कि जो cosine omega naught वाली टर्म है ना और जो cosine 2 omega naught वाली टर्म है वो दोनों मुख्तलिफ डिलेज के साथ ऐड होती हैं, राइट? एंड दैट्स अ प्रॉब्लम खासतौर पे ऑडियो के अंदर, राइट? ऑडियो के अंदर इफ दिस द सिस्टम डज नॉट हैव लीनियर फेज, different frequencies experience different delays when they pass through the LTI system, and that causes a lot of distortion and perception wise. Okay, so that's not desirable. So that's why we desire that LTI systems must be linear phase, especially for audio type of signals, right? I think there's somebody wanted to say something or unmute किया था किसी ने. Right. Okay. So we're almost 8 o'clock. I actually had lots of other exercises as well. We don't have time to do them. So let me just do one of those. Okay, and the other ones I'll just probably write these up in the same on the same page, and so you can try them on your own, and then ask me if you have questions. Okay, so here's the problem: x of t equals sine t convolved with the derivative of sine 2t divided by pi t. Right, evaluate this convolution. So what do you do? क्या ख्याल है? So if you start doing the convolution in the time domain, you're going to run into a lot of trouble, right? The first thing is you need to differentiate sine 2t divided by pi t. I mean, how do you do that? That's going to be extremely hard, right? So the answer or the trick to this is to go into the frequency domain and analyze this in the frequency domain, right? So you compute the Fourier transform of x, right? And if that turns out to be a form that's easy to look into, and then you take the inverse Fourier transform of x and see what should x of t be, right? So if I take the Fourier transform of x, what do I get? Easy in the Fourier domain. Right, so x of j omega, what is that equal to? Right, so let me give you some results, which is I am missing something here. So sine t divided by pi t here, yeah. So the result that we're familiar with is sine omega c t divided by pi t. If I take the Fourier transform for this, Fourier transform for this is a rectangular pulse. And this is an ideal low pass filter, by the way, right? So this is x of j omega, and x of j omega is equal to 1 from minus omega c to plus omega c, and the height is 1. So this is x of j omega, and this is x of t, right? So this is the result we know. Now, how do we solve this problem? Right, so x of j omega is equal to the Fourier of sine t divided by pi t multiplied by the Fourier of the derivative of sine 2t divided by pi t. क्या करूं मैं? So what is the Fourier transform of sine t divided by pi t? Let me just look at graphically sketch this. This is omega c is 1, and from 1 radians or minus 1 radians to plus 1 radians, the height is equal to 1. And this is being multiplied by the derivative in the time domain is equal to multiplication in the Fourier domain by j omega multiplied by, and this is minus 2 to plus 2, and the height is 1. What is the result that I get? If I just multiply these signals together, these two signals together, what do I get? Right, so this is multiplication is associative, right? So essentially this is what's going on.
So ये j omega और वो 1 by r रह जाएगा, and with minus 2 yes it would just be removed.
Minus 2 क्या हो जाएगा? चला?
minus 2 या वो it would be removed ना, क्योंकि 1 into उसके अंदर
Good.
वाला part is also.
Good.
So
Right,
just
so
1 वाला part रह जाएगा, बाकी 0 हो जाएगा.
right, so I'll do this by multiplying these two together first. ठीक है, j omega को भूल जाएंगे. If I multiply these two together, what I get is this thing from minus 1 to plus 1 multiplied by j omega, right? And the height is 1. So what would be the inverse Fourier transform of the x of t would just simply therefore be the derivative of the inverse Fourier transform of the rectangular pulse, which is sine t divided by pi t. And you can go ahead and evaluate the derivative for this. That's easy to do. ठीक है, वो division rule लगा दें. All right. Should I do one more? जी चलो.
सर sin 2t का भी तो इसी तरह होना था, डिवीजन रूल लगा के अगर हम करते, बट करंट पे हमने ऐड करना था उसको sin t over pi t के साथ.
फिर से बताइएगा. ठीक है.
अगर हम sin 2 या पार्ट हम इसको फोरियर में ना ट्रांसफॉर्म करते, sin 2t वजह का भी डेरिवेटिव ऐसे ही आना था कि डिवीजन रूल लगाते.
Okay, बिल्कुल.
डेरिवेटिव एड sin t over pi t.
Exactly.
So,
exactly. But then you
it would be longer.
would have had to compute this convolution after you took the derivative.
Oh, it was convolution. I thought.
Right. So the convolution करनी हो, derivative लेने के बाद नीचे square की value आ जाएगी, pi t squared है, ऊपर दो चीजों का difference है, right? And then when you're convolving, there's an integral.
Okay.
Right,
Actually,
so
I thought it was addition.
No, that's not addition. This is convolution. Right. So this becomes very easy to solve in the Fourier domain, and that's as we've seen. Okay. So I think I'm going to stop here. It's 8 o'clock already. And I also get the feeling most of the students are silent observers at the moment, right? So perhaps there's no use in me doing the more complex problems. And there are many, many other complex problems I had, or complex nahi kehna chahiye, sophisticated or difficult problems that I had in my notes. So I'll just put them up here, say, Kiji, these are exercises, do them on your own. Okay, if there are specific question you want to ask, go ahead. Otherwise, we can stop.
So the delta function की sampling property है.
Yeah.
I was really confused about it. जिस तरह अभी आपने किया था, उसमें, yeah, so it was pi into delta omega plus omega naught e raised to power j something.
Yeah.
So उसमें after we have used the sampling property, e में जो omega था वहाँ पर we put the value of omega is equal to minus omega naught basically.
Yeah.
So लेकिन delta stays there as it is.
Yes.
ठीक है. Delta वाला function it stays there as it is. लेकिन I've seen there are a lot of questions, especially जहाँ पर integral साथ लगा होता है.
Yeah.
After we have taken the integral, the delta disappears.
Yes.
So that is how the sampling property works. और ये जो delta disappear होता है वो integral की वजह से हो रहा होता है.
Exactly.
So, delta का integral will be 1.
Exactly.
That is only a case जहाँ पर delta disappear हो रहा है क्योंकि वो 1 हो जाता है.
Yeah, but otherwise, if there's no integral, so it stays.
अच्छा ठीक है क्योंकि I used to do this के integral में बाद में देता था and ठीक है.
Right? So लेकिन अभी ये जो सारा कुछ ये वाली चीजें देखी ना इस तरह करके, now I can for example build on top of it and say कि जी, I could for example ask you a question here and say कि जी, prove that if a cosine is an input to an LTI system of a certain frequency omega naught, prove that the output is also a cosine of the same frequency, in which the phase has been modified and the amplitude has been modified. I can ask this question, right? So this question is prove that if x of t equals cosine omega naught t plus phi is an input to LTI system with frequency response h of j omega, then y of t equals h of j omega naught absolute value times cosine omega naught t plus phi plus the phase of the frequency response evaluated at omega naught. अब ये वाली जो मैंने प्रॉब्लम दिखा दी, right? So the one that I've solved, that should be enough. I mean, if you really understood it, right? And that's the entire point. I mean, I was if you've really understood that, this should be a piece of cake, because it says utilizes the same ideas that we've done in that example. Okay, and let me urge you to try to prove this on your own. ठीक है, और यहाँ भी सैम्पलिंग प्रॉपर्टी डेल्टा की वजह से ही होगी सब कुछ. And I can list and go other exercises in the same document that you can practice.
Thank you.
ठीक है, चलिए.